Good day, viewers, and I want to welcome you to this tutorial class. Today we'll be taking on a very important concept in thermodynamics. For you to understand the concept of thermodynamics, there are two important terms, two important concepts which you need to understand, and that is what we want to deal on today. Those important concepts are heat and temperature. We have heat transfer, we have heat, and we have temperature. If time permits us, we might go into heat transfer, but we are going to basically look at heat and as well as what temperature. But if time permits, we dive into heat transfer. Okay, before we go into what we have proper, let us quickly look at the learning objectives. By the end of the lesson, the student should be able to define heat. They should be able to describe the relationship between heat and temperature. They should be able to explain the kinetic theory of matter as related to heat expansion as well. They should be able to mention the effects of heat, and they should be able to explain the following: linear expansivity, area expansivity, volume expansivity. And they should be able to explain the concept of temperature and how to measure the temperature of a given body, as well as conversion from one temperature scale to the other. So let us quickly move into what we have today. Now, when you look at the concept of heat and temperature, somehow they tend to have a very, very close relationship. Some cases, some students tend to misinterpret heat for temperature and temperature for heat. But the question is that heat and temperature, are they of the same physical quantity? Do they actually mean the same? Do they actually, is there any form of relationship between heat and temperature? So let us go into heat first. Now, the first thing I will have to let you know, when we come into different forms of energy, which we have studied earlier, when it asks you to state the different forms of energy, of course, you will state chemical energy, the electrical energy, you state some few energies, but then you will also state heat energy. So what does this simply mean? It simply means that heat is a form of what? Energy. But what form of energy is heat? Okay, heat as an energy has to do with the internal energy of a body, or the energy which is due to the intermolecular forces within the molecules of the body. Okay, in summation, gives you what we call the internal energy, which is referred as what? Heat energy. So heat is a form of energy, but this form of energy is due to the form of energy, but this particular energy can flow from one point to another. And why does it flow from one point to another? The reason why it flows from one point to another is due to a temperature difference. Okay, so if there is no temperature difference, there won't be any flow or any form of flow of heat or energy. So if you have a temperature that is what, let's say 50 degrees Celsius, and you have another point, let's say 100 degrees Celsius. So that means there is going to be a flow of heat energy because there is a temperature difference. There will be a flow of heat energy from one point to another point, from the point where you have a higher temperature to where you have a less temperature. That means it will flow from 100 degrees Celsius to 50 degrees Celsius. But this flow of energy will continue just like that until you get to a point where there is going to be a uniform distribution of heat energy, such that the temperature becomes uniform, and when the temperature becomes uniform, there is no flow of heat energy any longer. So what then do we call that condition? What then do we call that state in which there is no flow of heat energy in the body due to the uniform temperature of the entire body? That particular condition is referred as thermal equilibrium. So when they say a body is at this thermal equilibrium, it means that there is no flow of heat energy. It means that the temperature of that body is uniform in every part of the body. So since heat is a form of energy, so what then is the unit of heat? The unit of heat is simply joules. unit for heat is simply what? Joules. So then let's move down to temperature. What then is temperature? Okay, temperature simply tells us that how hot or how cold an object is. So that is why we say that temperature is the degree of hotness or coolness of a body. Okay, so and it determines the flow of heat energy. So if the temperature of a body differs, there will be a flow of heat energy. But if the temperature of a body is the same, okay, it's at equilibrium, that means there won't be any flow of heat energy. All right. So one thing you need to know is that if both heat and energy have you cannot distinguish them, that you can distinguish them anyway, but they work relatively with each other. They are a function of themselves, in the sense that you cannot talk about heat without talking about temperature. You cannot talk about temperature without talking about what? Heat. Okay, energy flows from one point to another due to temperature difference. In other way around, there is going to be an increase in temperature if there is an increase in in heat energy. Then there will be a decrease in temperature if there is a decrease in heat energy. So for every object, for everybody, they have molecules. There are molecules, okay, and the molecules of this object, from kinetic theory of matter, they are always in motion, okay. But when there is an increase in energy, there will be an increase in the movement of these molecules. In other words, that means there will be an increase in the speed of these molecules. Okay, so but the average kinetic energy, since there's an increase in the body, that means they gain more kinetic energy. So the average kinetic energy of those molecules of the body is a measure of the kinetic is the measure of the temperature of that particular body. So the SI unit for temperature is Kelvin, or is degree Celsius, of which this can be converted from degree Celsius to Kelvin, and Kelvin to Celsius, or to some other scale to other temperature scales, which we are going to look at later. Now we have what we refer as thermal conductivity, which has to do with the ability of materials to allow the flow of heat energy in them. So every materials have their own thermal conductivity. Okay, so if your thermal conductivity is high, that means the body has a greater ability to allow the flow of heat energy to pass through them. So, but that is not what we are going to look at today. So let's quickly dive into the difference between heat and temperature. Okay, first we have that one. I said earlier that heat is a form of energy. All right, heat is a form of energy. Fine, but temperature itself is not a form of energy. It's not a form of energy. Okay, and when you look at the instrument as well, you can use the instrument again to differentiate them. For heat energy, the instrument used to determine heat energy is referred as is calorimeter, while that for temperature is thermometer. Okay, and for temperature, using a thermometer, the really can be determined directly. But in all cases, for using a calorimeter, there have to be some form of calculation or thereabout before you obtain the actual value of heat energy that is being involved. Okay, when it comes to the unit, the SI unit for heat is joules, and for Kelvin, for temperature, we have Kelvin, degree Celsius, we have Fahrenheit, rest of them. So, as I said earlier, temperature does not flow, but heat energy would flow. So there are several differences between heat and temperature, which tells us that they are not the same. There are two different concepts, heat and temperature. Okay, let's look at some of the kinetic theory of matter that has to explain heat and temperature. As I said earlier, every matter is made up of particles, and these particles are in constant motion. They are in constant motion. But what do you think if we have more energy, heat energy, into this body? Okay, there is more heat energy into this body. What does this simply mean? Or maybe if the temperature of the body is being increased, what happens to this body? What happens to the energy in this body? You find that the molecules of this body, the speed increases as the temperature increases, the speed increases, the motion of the molecules of this matter increases, moving either randomly or translationally, like that, continuously. Okay, but when you reduce the temperature, the heat, the energy within also what reduces, which is seen in terms of the vibration. The vibration of the molecules reduces, the speed of the molecules what reduces, which tells that what the kinetic energy has reduced as well, and resulting to the what decrease due to the decrease in what the temperature. So if the temperature is increased, the speed of the molecules increases, the kinetic energy of the molecules what increases as well. So the particle energy is determined by the temperature, which affects whether a substance or matter exists in solid, liquid, or what gaseous state. So this explanation actually tells us if this matter can what expand. It can also be discussed in terms of the expansion of matter. It can be discussed in terms of what of the average kinetic energy of the what body. So that is why we say that what temperature is a measure of the average kinetic energy of the body. As the temperature increases, the average kinetic energy of the body increases, which results to the what to the speed, to the increase in speed of the body itself. Okay, some of the effects of heat. We are going to discuss some of the effects of heat. Now, the first one we need to discuss is what is change in state. Change in state of what a body. Yes, you agree with me that yes, that matter exists in what we have the what solid, we have the liquid, and we have the what gaseous what state. So this matter can change from one state to the what other, and for them to change from one state to the other, they require what heat, either the addition of heat or the removal of what heat. When you add heat to a solid, it changes to what liquid. When you add heat to liquid, it changes to what to vapor or to gaseous. But when you remove it, the reverse what occurs, or the reverse what takes what place. But when you are to change matter from one state to another, there is a particular form of heat that is required for it to change from one form to the other, and that heat is referred as what the latent what heat. The latent heat. This latent heat is referred as what the hidden what heat. Why is it referred as the hidden heat? The reason being that all molecules are held together by a force, by a bonding force. Okay, so when heat is applied to that body, the temperature what increases as heat is being applied to the body. But it will get to a point that the temperature no longer what rises, but yet heat keeps on what is being what supplied, is being what added to the body. So the question there is that what happens to the what to the heat that is being supplied or is being added or is being given to that body? Okay, at that constant temperature, heat is added to the body, given to the body, yet the temperature is not what is not increasing. So what then is happening to the heat? Where is the heat there? Now that particular heat given to that body, where there is no increase in temperature, is used in breaking of those bonds, those force of attraction that is holding the molecules of that substance or matter together. So that hidden heat that is being supplied, where there is no increase in temperature, is used in breaking of those bonds. So that is why we refer that latent heat as hidden heat. It is hidden because the temperature was not increasing, whereas heat is being supplied. So the heat is used in breaking of those bonds. Okay. So we have Q. Q is given as the latent heat of latent heat, and the unit of latent heat is in joules. We have M. M is what the mass of the body, okay, in kilogram. Then L is the specific latent heat in joules per kilogram. Please, I want you to take note of this particular equation. Q is equal to ml. Okay, it is the heat needed, the latent heat needed to do what? To change matter from one state to the other. Remember, if you are changing the state of matter from solid to what? Liquid, the earlier is referred as what? Latent heat of what? Fission. But if you are changing it from what? From liquid to what? To vapor, or vapor back to liquid, it is referred as what? Latent heat of what? Of vaporization. Latent heat of what? Vaporization. So take note of this formula again. Q is equal to what? ml. We might use it in solving one or two questions in slides, or perhaps in the quiz that we are going to present to us later. So that is the change in state of what? Matter. Take note that latent heat is referred as what? The hidden heat. It is the amount of heat needed to change a substance from one state to another at constant temperature. Underline that word must be there, at constant or temperature. Why? Because there is no change in what? In temperature. Now the next one is what? Yes, heat. One of the effects of heat is that heat changes temperature. It causes what? Either the rise or fall of what? temperature. Okay, when heat is added to a body, the temperature will increase. But when heat is withdrawn or is being removed from the body, the temperature will falls. Okay, so as I said earlier, that temperature is a measure of the average kinetic energy of a body, and to rise the temperature of an object, you have to put energy into the object. Okay, so now let's look at this important formula which I have here, that Q is equal to MC change in temperature. What does this Q stand for? What does the M stand for? What does the C stand for? And what does this change in temperature? Whenever you see this sign delta, it means change in temperature. Okay, the Q, of course, stands for what? For the quantity of heat needed to change the temperature of a body. When you want to change the temperature of a body, heat is required. Then the M stands for the mass of the body in kilogram. Then C is the specific heat capacity of that body, which has to do with the nature of the body per se. The heat is called what? The heat or the thermal capacity of the body. Please take note of that unit. The specific capacity is joules per kilogram per Kelvin, while heat capacity is joules per Kelvin. But then what is this heat capacity? It is the amount of heat needed to rise the temperature of a body by 1 Kelvin. The amount of heat needed to rise the temperature of a body by 1 Kelvin. But when you talk about specific heat capacity, it is the amount of heat. Specific capacity is the amount of heat required to change the temperature of 1 kilogram. That is why we have per kilogram in this minute. The amount of heat required to rise the temperature of 1 kilogram of a body by 1 Kelvin. That is specific heat capacity. Then take note that your heat capacity, which is the amount of heat needed to change the temperature of a body by 1 Kelvin, is also given as mass times specific heat capacity. That's MC. So it means that in this formula we have Q is equal to MC, change in temperature. This your MC is equal to your heat capacity or your thermal capacity. So when you substitute that H for this MC, we can as well have Q is equal to H delta theta here. Okay, so please take note of this, right? Involve it in solving questions. Q is equal to MC change in temperature, which has to do with the amount of heat needed to change the temperature of a body. Okay, which is equal H delta theta. Then take note of this. For changing the temperature of a body, okay, heat capacity is involved, okay, in the formula. But when you have to change the state of a body, your mind should go to latent heat. Okay, and there is no change in temperature when you talk about latent heat. Is that taken? All right. Okay. Okay, so let's move to the next. Now, changing the shape. Yes, heat can cause the change in shape of a body. Okay, if an object contains two substances with different linear expansivity, so those substances has different linear expansivity, which we are going to discuss. Linear expansivity, okay, has to do with the change in the linear expansion, change in the area expansion, change in the volume expansion. So the material that has a greater expansivity or linear expansivity increases faster than the one that has less expansivity. Now this aspect of change of linear expansivity, that is change in the shape, is being applied when it comes to losing of knots or tightening of knots. It comes to play when they talk about the bimetallic strip, thermostat, and the rest of them. Even in your fire alarm system, that is an advantage of expansion, linear expansivity, basically. Okay, in your chemical reaction today, fine. Heat is is being applicable there. So heat can start up chemical reaction, just as you have in your matchstick here. In the matchstick, yes, it can cause such reaction to occur. Okay, so this can be caused by breaking bonds between atoms, starting a reaction with nearby substances, or changing the valency of the substance. So when this occurs, of course, heat comes into play. Yes, the density, yes, heat as well can cause density. Heat can cause density. When heat is added to a body, when heat is added to a body, you find that the density of the body will do the density of the body will reduce. Okay, so heat lessens the density of the body, but when heat is being extracted or being removed from a body, the density of that body increases. Okay, as you have it here, as a substance gets hotter, its atoms vibrate more strongly and take more space. Okay, most substances get bigger as they get hotter, because their mass stays the same. They become less dense. We usually measure this by how much a substance expands in one dimension, either length, width, or height, for each degree for Celsius. It increases in temperature. This is called the coefficient of thermal expansion. Mr. Okay, now let's look at thermal expansivity. Okay, for thermal expansivity, okay, it has to do with an increase in the size of an object when heat is applied. So when the heat is being applied, the molecules gain more kinetic energy to enable them overcome the thermonuclear forces. Then the molecules now move apart from each other. So when the molecules move apart from each other, it results in an increase in the average distance between molecules. Okay, so there is an increase in the average distance between molecules. So this average distance between molecules it results in the increase in the size of objects. But you need to know that different molecules have their own different thermonuclear forces of attraction. There are some that have a stronger thermonuclear force. There are some that has a weak thermonuclear force. Those that have a strong thermonuclear force requires much heat energy to break that bonds and to enable or to make the bonds get weaker, such that their average distance between them might get increased. But then, if a molecule should have a strong thermonuclear force, the expansion between them, the average distance between them will be small, will not be so large. So take note of this: a stronger thermonuclear force between the molecules of substance we result to greater amount of energy if it wants to expand further. Okay, but then at a constant heat that is being supplied, the molecule that has a stronger thermonuclear force will create a smaller expansion. Then of course those that have a weak thermonuclear force will create a larger expansion. So what I've just said now is kinetic molecular theory explaining expansion. So expansion can occur in solid, it can occur in liquid, it can occur in gas. But we are basically going to look at expansion in solids. Okay, have this in mind. As I said earlier, when heat is added to solid, they expand, but when they are being removed, they contract. Okay, take a look an idea of someone that is standing under a metal roof. Okay, in the sunny day, the person hears some crack sounds. Then in the evening, the person also hears the same crack sound. And what does that sound entails? In the afternoon, there is this crack sound indicating that the zinc roof is expanding. Then in the evening, you hear the same crack sound, which tells you that the zinc roof is contracting. So several materials have their own different expansivities. Okay, several solids, several materials, they have their own different expansivities. Okay, and expansivity in solid occurs in three different dimensions. Okay, it occurs in one dimensional, that is just the length alone, which is referred as linear expansivity, as we have here. Then it also occurs in two dimensional, which is referred as your area expansivity or your superficial expansivity. Then it occurs in the three-dimensional, that is the whole volume, the whole part of the body expanding, which is referred as the volume expansivity or the cubic expansivity. Okay, let's start with linear expansivity. Of course, as I said earlier, it has to do with the expansion of solid in one dimension. Okay, just the length expanding. So the linear expansivity of a material is defined as the increase in length per unit length for each degree rise in temperature. Is the increase in length per unit length for each degree rise in temperature. So this is what we have. This is the symbol for linear expansivity. We can have it here, L2 minus L1, which has to do with the change in length. L2 is your new length when the heat is being applied or being removed, while L1 is the old length or the initial length. So when you subtract L2 minus L1 when heat is added, or L1 minus L2 when heat is removed, what I have is simply means a change in the what length. L1 is your original what length. Okay, so the increase in length over what the original what length times the what temperature what difference. So as I said earlier, linear expansivity of a material is defined as the increase in length per unit length for each degree rise in temperature. And the SI unit for this expansivity generally is what is per Kelvin. Whether linear expansivity, area expansivity, cubic expansivity, their SI unit is what is per Kelvin. So the first question under this, still on linear expansivity, the first question says, explain the statement the linear expansivity of brass is 2.0 times 10 raised to the power minus 5 per Kelvin. Explain the statement the linear expansivity of brass is 2.0 times 10 raised to the power minus 5 per Kelvin. So the explanation to this is that the statement means that the length of 1 meter, length of brass will increase by 2.0 times 10 raised to the power minus 5 meters when its temperature is increased by 1 degree Celsius or 1 Kelvin. Number 2 question under linear expansivity. It says a copper rod whose length at 30 degrees Celsius is 10 meters is heated to 50 degrees Celsius. Find its new length, that is L2. Find its new length. Take alpha, that is linear expansivity, forward copper as 0.000015 per watt Kelvin. Now the first thing we have here from our given parameters, we have the length, which is L1, 10 meters, but that length is at that temperature, it is 30 degrees Celsius. So the second temperature, 50 degrees Celsius, what is the new length? So from my formula we have here, okay, what we just simply did here was to make L2 subject of the formula. But you can solve this, I go ahead and solve this by substituting directly. Okay, substitute directly and having this value for L2. This is my linear expansivity, 0.000013 per Kelvin. Then here, L2, I'm looking for L2 minus L1, which is 10. This is 10. Then the change in temperature is what, 20. Then when you solve for L2, you eventually get your value 10.0034 meters. Or you can simply make L2 subject of the formula for what we have here, then plug in all your given parameters, and that is it. The next is what area expansivity. The area expansivity is represented by the what? By the symbol beta. So it is the what increase in area per unit area per degree rise in temperature. It's the increase in area per unit area per degree rise in temperature. So that is your area expansivity. Okay. So the formula for your area expansivity just the same as that of your linear expansivity. So the only difference there is that the A over there for linear you have L, for area you have A, for cubic you have what V. That is just the difference. And that difference is their relationship. The relationship between what beta and what, that is area expansivity and what linear expansivity. Look at one of the relationship here. You might be giving your linear expansivity. So what is the relationship between linear expansivity and area expansivity? It is what your area expansivity is twice your what linear what expansivity. That is your beta. That is beta equal to what 2 what alpha. That is what we have here. So this is the formula of what we have here. Then this change in temperature of course gives us this. Okay, we can easily show that the area expansivity of superficial expansivity, which is B equal to what beta equal to what 2 alpha, where alpha is the linear expansivity of the what material. So now an example here we have that the linear expansivity of the metal is 0.000019 per Kelvin. What will be the area of 400 millimeter watt square be if its temperature is raised by what 10 degrees Celsius? Okay, so the temperature is given already, the change in temperature, which is what 10 degrees Celsius. Then of course, do not be scared of this formula you have here. It's just like your previous formula that we have here. All what we did here is to make the A2, so that is the new area subject of the formula. Then don't forget that whenever you now see your beta, you now have what your 2 alpha. That is just it. Make this A2 subject of the formula, the new area subject of the formula. Then when you are done making it submit on the formula, whenever you see your what beta, just have your 2 what alpha, that is 2 times the linear expansivity. So that is what is done here. Making your A2 submit on the formula is what I have. Okay, then this my beta is equal to what? 2 what alpha. So all the what I have, I just substitute into them. Okay, then by the time I solve, my answer, because you can see that I worked with what millimeter what square, so my answer should be in millimeter square as well. If it's in centimeter square I'm working with, it should be in what centimeter what square as well. Okay, volume what expansivity. The volume or cubic expansivity symbol is what gamma, is the increase in volume of a substance per unit volume per degree rise in what temperature. The formula, as I said earlier, still remains the same. Change in volume, that is V2 minus V1. Then I have V1 change in temperature. So you can still make V2 so the formula, as I said earlier. But whenever you see your gamma, the relationship between your gamma and your what linear expansivity is what is thrice that of linear expansivity. So the gamma I have here is equal 3 times alpha, that 3 times linear what expansivity. So you can see that volume has to do with what the expansion of all parts, all ends, 3-dimensional what expansion. This end is expanding, here is expanding, this other is expanding. The whole body, the entire what body is what is expanding. So the question we have here: a brass cube 10 centimeter is heated through 30 degrees Celsius. If the linear expansivity, consider linear expansivity is given 2.0 times 10 raised to the power minus 5 per Kelvin, what is the increase in its volume? So this is a tricky one. You can see that the volume is not given, rather the side of the cube is given. And when you talk about the cube they have all sides what given. And what then is the volume of a cube? The volume of a cube is what is 1 of the length raised to the power 3. Okay, so as we have read that the volume of the cube, x raised to the power 3, and my x is given as what 10 centimeter. So what then is the volume of the cube? The volume of the cube, when I solve, I'm going to have what 1000 centimeter what cube. So since this volume is obtained from the initial length, so that means the initial volume is what, that V1 is 1000 centimeter what cube. Then we are asked to determine the what increase in what in the volume. So what then is the increase in temperature? The increase in temperature is 30 degrees Celsius, because it said it is increased through or increased by. So that simply gives you what increase in what temperature. Now look here, we have the linear expansivity of brass. This is the linear expansivity of brass, which is clearly stated here. But do I really need the linear expansivity of brass? No, because I'm to use this formula, that my volume or cubic expansivity is equal change in volume over what V1, which is my initial volume, change in temperature. So how do I now get my what cubic expansivity? My cubic expansivity is equal 3 times the linear expansivity, which is what I just figure out here. Key it into this place, then I now have my 6.0 times 10 to the power minus 5 per Kelvin. Then come down here, make my what change in volume, the increase in volume, so that the formula. And then make it so that the formula, you now key in the necessary what parameters. My cubic expansivity, which is 6.0 times 10 to the power minus 5, my V1, which is what 1000, and my change in temperature, which is what 30. So quickly check, solve, and see if your answer tallies with this 1.8 centimeter what cube. Okay, temperature and its measurement. As I said earlier, you can't do without temperature. Heat, they have a very strong what functions or relationship, which one you cannot discuss one without the other. Okay, so having discussed about heat, so let us quickly look at what temperature and its measurement. Quickly on the first note, there are two what fixed point of a thermometer. Thermometer is generally used for measuring what temperature, and for every temperature what scale, they have two important what points of a thermometer. We have the upper fixed point and we have the what lower what fixed point. So what then is the upper fixed point? The upper fixed point is the temperature. Please, whenever I hear any terms of point in physics sciences, it's referring to temperature. Boiling point, dew point, melting point. The term point refers to the word temperature. So lower fixed point is the temperature of pure melting ice at normal atmospheric pressure. And what is that normal atmospheric pressure? Is 760 mm mercury. And that word that can be used for what lower fixed point is what ice point. Please, all ice points are meant to what 0. Don't be confused with that. My ice point is always was 0 for degree what Celsius was scale. And when you talk about the upper fixed point, it is the temperature of steam from pure boiling water. Please, it is not the temperature of pure boiling water, it is the temperature of steam, because that steam is the purest form of water. So you are taking the temperature of steam and not the temperature of the boiling water. So the temperature of steam from pure boiling water at normal atmospheric pressure of 760 mm mercury. And that term for what upper fixed point is called what is steam point, which is 100 degrees Celsius. Okay, so you might see some question, they might have what minus 10 degrees Celsius, 0 degrees Celsius, 100 degrees Celsius, 120 degrees Celsius, and they will ask you what is the lower fixed point, what is the upper fixed point. Of course, minus 100 degrees Celsius is lower than that 100, but than 0 degrees Celsius. Your answer still remains 0 degrees Celsius. Lower fixed point for degrees Celsius is always 0. Upper fixed point for degrees Celsius scale is always 100 degrees Celsius. Then the difference between your fixed point, lower fixed point, and upper fixed point is referred as your what? As the fundamental what? Interval. Okay? Between the upper fixed point and the lower fixed point of all temperature scale is referred as what? The fundamental what? Interval. So the instrument I have here is the instrument that is used. The instrument that is used to determine the upper fixed point, the hypsometer, and this is what the setup to determine the lower fixed point of what? Pure melting ice. So, as I said, we have different scale of temperature. Okay, we have the degree Celsius, the degree Fahrenheit, the degree Rankine, the Kelvin what? Absolute scale temperature. They all have their what? Upper fixed point. Look at it, that of degree Celsius. Okay, that 100 degrees Celsius. That of what? Fahrenheit, the upper, you have it 212, the lower is what? 32, and they all have that of Rankine and so on. But you can be asked to what? Convert one temperature scale to the other temperature scale. Now here I have a very simple format for you to use. Now this is degree Celsius, the scale, minus lower fixed point, all over the fundamental interval, equal to what? Kelvin minus what? Lower fixed point, all over the what? Fundamental interval. So you can see equate it to what? Fahrenheit minus the lower fixed point, all over the fundamental interval. Then Rankine minus the lower fixed point, all over the fundamental what? Interval, just like that. So if I'm giving a scale in what? Fahrenheit to convert to what? Degree Celsius. What do I need to do? Fahrenheit to degree Celsius. This is degree Celsius. I will connect it to what? Fahrenheit. If this is degree Celsius minus lower fixed point all over fundamental interval. I will come over here because I'm changing to Fahrenheit. I will say Fahrenheit minus what? Lower fixed point all over fundamental interval. They all have their fundamental interval. For Fahrenheit, the fundamental interval is 180. For degree Celsius, Kelvin scale, it is 100 what? Degrees Celsius. That is why the change in temperature for Celsius and what? Kelvin is always what? The same. Okay, thermometric properties. These properties are those the properties of the liquid that responds to the change in temperature in thermometers. They respond to the change in temperatures in thermometers. So, for instance, you have the liquid in glass thermometer. The liquid in glass thermometer. What is the thermometric property? What is the effect of those liquid to temperature? That is what we mean by thermometric property. So, for liquid in glass thermometer, you are talking about what? The change in what? The volume expansion of what? Of the liquid. Volume expansion of the liquid with temperature. Either the volume expansion or the change in the volume of the liquid with temperature. So we have for what? Your gas thermometer as well. Okay, for constant volume gas thermometer. For constant volume gas thermometer, we have what? Change in the volume of the gas. We have change in the volume of what? Of the pressure at constant volume with temperature. Okay, so we have what for what? Thermocouple, which has to do with what? Change in the EMF. Okay, at the junction, between the junction of the terminals of the what? Of the thermocouple with change in temperature. So they all have their what? Thermometric what? Property. For resistance thermometer, we have the change in resistance, in the length of the what? The change in resistance of the thermometric what? Substances with change in what? Temperature. So all these, the response of the thermometric substances with temperature gives you the thermometric what? Property. When you talk about the thermometric substances, you're talking about the substance, that substance in the thermometer that changes with temperature when heat is what? Added or what? Being removed. For instance, for liquid in glass thermometer, we have mercury, we have alcohol. Okay, there are some cases that mercury are preferably used as what? The liquid for the liquid thermometric what? Property in liquid in glass. There are so many reasons. Reasons being that it can be used for measure what? Higher temperature. Okay, since it has a a boiling point of 359 degrees Celsius, but disadvantage cannot be used to measure what very low temperature. Okay, it cannot be used to measure what low temperature. Okay, then when you talk about that of what do you call it, alcohol cannot be used to measure what high temperature, because the melting point, the boiling point for alcohol is 78 degrees Celsius. So that is why mercury has an advantage over it. But it can be used to measure melting what lower melting point, because its melting point is about what minus 115 degrees Celsius. So you can see that some of these liquids have their own advantages and disadvantages for being used as thermometric substances. Okay, so here we have the liquid in glass thermometer. Now what I have here is the laboratory thermometers. Their steam point always 100 degrees Celsius, while ice point still remains 0 degrees Celsius. So please take note of these kinds of questions when you meet them. You might see they might calibrate this to this point and have minus 10. Calibrate it to this place and have 120, and they will now ask you what is the steam point, what is the ice point. Please note, your steam point, no matter how being calibrated, your ice point is always 0 degrees Celsius, and your steam point is always 100 degrees Celsius. Okay, the clinical thermometer, very important thermometer, and it has its own unique features. One of the unique features is that it has a constriction. Okay, most times when you go to the hospital and they make use of this, before using this, your nurse has to do has to shake it so well, so that the mercury we have to run down into this bulb, and by the time they now measure the thermometer temperature with it goes up to a particular point and remains there, does not come down. This little constriction, constriction, do not allow the mercury from running down back to the bulb. So the only way you can make it run back to the bulb is when it is now shaken and properly it goes to the bulb. And most times the tube here is always a narrow capillary tube, which allows for a large linear expansion for a little temperature difference. For a little temperature change, there's going to be a wide linear expansion. Okay, then most importantly, it gives a short range of temperature, see, between 35 to 42 degrees Celsius. See, this is one of these important features here. Okay, so we have the gas thermometer, which makes use of gas. Some of the gas used here are we have nitrogen, helium, hydrogen are being used as the gas in here. There are some calculations. You might not get the temperature directly when you use such. You do that by interpolation method. Some little calculation that be involved. The volume where the gas is being placed is always constant volume. Okay, but it gives a very accurate measurement of temperature. Only the very accurate measurement, only that it is very cumbersome. It is very complex. It's not portable. Okay, in presence of taking it from one point to that point, it can get shattered. So the thermocouple, very important, very nice thermometer, okay, which can measure very high temperature as from 500 degrees Celsius to 1500 degrees Celsius. So it simply works with the principle of thermoelectric effects between dissimilar wires. So some of the wires that can be used for this are nickel, we have Constantine wires, coppers, and so on. Okay, and it's very, very sensitive, very, very sensitive. Those small, but very, very sensitive. So we have others like the bimetallic strip thermometer, we have the resistant thermometer, we have the pyrometers. Okay, so guys, why not we quickly just look at these questions we have here and discuss on them quickly. It has to do with what we have just discussed on heat and temperature. Let's test our evaluation. Let's check our understanding on this little aspect. Though question is not much, but it can go a long way. So number one says the ice point of the absolute scale temperature is. So how would you answer? How would you answer such? How would you answer such question? Let's say the ice point. Now, if I don't know the ice point of absolute scale, your absolute scale temperature is always the Kelvin scale temperature. If I don't know the absolute scale, the ice point, if I know that of the Celsius scale, what do I simply need to do? I just simply interpolate and convert the 0 degrees Celsius to the absolute scale temperature. and that is it. Okay, so you can interpolate for the Celsius scale. You can take any, okay, your 0 scale, which is the ice point for Celsius scale is what, 0 degrees Celsius, while that for a Kelvin scale is what, 273. Okay, so if you want to convert from Celsius to Kelvin, so whatever you have in your Celsius, add it to what, 273. If you have what, 20 degrees Celsius and you want to change to Kelvin, you can simply add the 20 degrees Celsius plus what, 273. It's a very simple way of going. But you can use the interpolation method which we have in the slide given to you. Okay, the next question. A 40 thermometer registers what, 102.5 degrees Celsius at what, 100 degrees Celsius. If the thermometer has no zero error, what will it register at 55 degrees Celsius? So this is a very nice one. You can use the interpolation method. Okay, and let me just give you some little time to see what you can come out of this. But one best way of doing this, one nice way of doing this is using your interpolation method. And that interpolation method, you have your degrees Celsius. Okay, just follow this cursor. This is my degrees Celsius. Okay, this point here is what, 0 degree, and this end here is what, 100 degrees Celsius. So you relate your 0 degrees Celsius down to the 40 thermometer. It said it has no zero error, so that means that ice point of the 40 thermometer is still what, 0 degrees Celsius. Then the steam point which of the Celsius scale, which is 100 degrees Celsius. So if you relate it down to the 40 thermometer, it is now 102.5 degrees Celsius. So we are now asking, what then will now be the 55 degrees Celsius? What will it register in the what? In the thermometer, the weight thermometer. So you just interpolate. You just simply say that, okay, from my, okay, this is what will it register at 55 degrees Celsius, that the 40 thermometer. So you say the value here, 55 minus what, 0, all over what, 102.5 minus 0, equal to what, x. That is the corresponding value of this in your normal thermometer, to your x, okay, minus 0 all over 100 minus 0. And the movement, so for x. And in the long run, I'm sure you have 56.14. So number 3, which of the following types of thermometer can be used to measure a range of temperature from minus 50 degrees Celsius to 50 degrees Celsius? So what kind of temperature can we use to measure this? Is it clinical thermometer? Is it mercury in glass thermometer? Is it alcohol in glass thermometer? Remember, your clinical thermometer should be out of it. Why? I think the range for your clinical thermometer should be from what, 35 degrees Celsius to what, 43 or 45 degrees Celsius, thereabout. So it is out of this sort of range. So let us go to the mercury in glass thermometer. For the mercury in glass thermometer, can we use this to measure a lower fixed point using the mercury in glass? Mercury in glass, of course, lower fixed point should be, it's not, minus 39 degrees Celsius. So we cannot go lower than that to this point for mercury in glass. Though we can use it to measure this point here, because the mercury in glass can measure up to this point, but we cannot use it to measure lower than this. So mercury in glass is out of it. What about your alcohol in glass? For alcohol in glass, we can use it to measure as low as minus 115 degrees Celsius, as you see here. Then what about the boiling point? Yes, the boiling point of alcohol is 78 degrees Celsius. That's above this particular point. So I think we have figured out our answer already. So we can go for C. Okay, number 4. The ice and the steam points on a mercury in glass thermometer are 10 centimeter and 30 centimeter, the ice and steam point respectively. So this is the ice point and this is the steam point. So by method of interpolation, which we are going to see later, calculate the temperature in degrees Celsius when the mercury meniscus is at 14 centimeter mark. Okay, guys, quickly use the method of interpolation and tackle this question. First, sketch down your degrees Celsius scale, have your 0, your ice point here. Then at the steam point, you have your 100. Take another scale. At the 100 steam point, you have the 30 centimeter mark. Coming down at the steam ice point, you have the 10 centimeter you have the 10 centimeter what? Mark. Okay, steam point 30 centimeter mark, ice point 10 centimeter mark. So they are not asking what is the temperature when the mercury is at 14 centimeter. So your interpolation method. So here I have my interpolation. The 14 mercury mark should correspond to the x here. So x minus 0 all over 100 minus 0 equal to 14 minus 10 all over 30 minus 10. Then you solve for x. So my answer on this should be okay. Let's go for A. All right. So number 5. What do we think that this answer should be for number 5? Somewhat tricky. You have to be very careful not to pick the wrong one. Okay. Number 5. Which of the following cannot be used to measure the temperature of what? A substance. So here you can see that we're talking about what? Thermometric property. The first one, we have that what? Of course, there's going to be variation of pressure when it comes to what? Constant volume gas thermometer. And variation of pressure. There's expansion of liquid when it comes to liquid in glass thermometer. So what about C? Change the resistance of a conductor. So what about the thermocouple effect? Change in the EMF with temperature. So what then is the answer here, guys? Which of the following cannot be used? So if you say that A, then you are wrong, you are not right. Then B, you are not right. C, you are not right. D, you are not right. Everything here, option A to D, can be used to measure the temperature of a body. They are good what thermometric property. A is for what? Constant volume in gas thermometer. B is for what? Liquid in glass. C is for resistant thermometer. Thermocouple is for what? Thermocouple effect for thermocouple. So everything here is correct. So the answer is nil. So better say is better for you not to put your option. Okay. In some cases, you might be tempted to pick something and you miss it up. So C. Number 6. What is the quantity of heat required to increase the temperature of 300 grams of aluminium cube from 30 degrees Celsius to 70 degrees Celsius? The specific capacity of aluminum is given as 900 joules per kilogram per Kelvin. So remember when I told you that when it comes to the change in temperature, the formula is being applied, and the formula is Q equal MC change in temperature. So let me quickly leave you some few minutes to attempt this question. Okay, all right. Then don't forget to convert your 300 gram to what? Kilogram. Change the temperature 70 degrees Celsius minus 30 degrees Celsius. We have what? 40 degrees Celsius. So we now impute it into the formula Q equal MC change in temperature. M is my what? 300. When you change it to what? To kilogram, you have 0.3 kilogram. Then my specific capacity 900. Then my change in temperature 40. Then when you solve this, you are going to have in joules 10,800 joules. Convert it to kilojoules and pick your answer. B. Okay. Number 10, the final one we have here. How much heat is required to change 3 kilograms of ice at 0 degrees Celsius to water at the same temperature? The same temperature, 0 degree ice, water 0 degree ice. So you can see that there is no change in temperature. So when there is no change in temperature, the heat involved where there is no change in temperature is referred as what? The latent heat. So how would you determine your latent heat? It is given as what? Q equal to what? ml, mass times specific latent heat. So your mass is 3 kilograms, and what then is the specific latent heat of what? Fission of ice, because ice is changing from what? From ice to what? Water. So the latent heat of what? Fission of ice. Okay, let me give it to you so that you can impute it and get your answer. The latent heat of fission of ice is given as 336,000. Take it again. It's given as 336,000 joules per kilogram. Okay. So since the latent heat required to change 3 kilograms of ice to water is given as ml, M is your mass, that is 3 kilograms, and L is what specific latent heat of fission of ice, okay, which is 336,000 joules per kilogram. Okay, fix and solve. When you fix it, solve it quickly, and what did you come out with? Okay, I think C is probably the right answer that we have here. Okay, so viewers, we have gone through through heat and temperature. As I said, there will be much time for us to go into heat transfer. I would have loved to, but let's keep that for some other contacts. So from your heat, difference between heat and temperature. Heat as a measure of the internal energy of the body, then temperature as a measure of the average kinetic energy of the body. We looked at the kinetic theory of matter that has to do with as in relation to to temperature, as in relation to energy, as in relation to expansion. We also went further to discuss about expansion of substances, where we now emphasize more on expansion of solids. Expansion of solids. So we now dive into the linear expansion in one dimension, expansion in 2 dimensions and 3 dimensions of solids. Though we still have some of the advantages of expansion of solids, which I mentioned here, but though not reading on the slide, but I mentioned it. Fire alarm system, removal of cork, tight cork of a bottle, and some of the application, that is when you talk about the creation of safety gap by engineers when making of bridges and so on. So from there we now went into solving problems in linear area and cubic expansivity. We dived into temperature and its measurement. We talk about the change of temperature scales, and then solving some other problems under temperature. So in my next class, hopefully, God's willing, I might go into heat transfer if need be. But for now, let's draw the curtain for today's class. May you are all blessed, and thank you for listening. My name still remains Mr. Uche. Thank you.